Okay, so in this last chapter here, 13, simplifying and solving radicals. Radical equations and the solving part, obviously. All right, so you need to remember you're looking for perfect squares that go into it. So we have 4, 9, 16, 25, 36, 49, 64, 81, it's 8, 9, and 100. And you can just keep going. So at 99, I should recognize that my times table is of 9 times 11. That should be easy right there. So square root of 9 breaks down to 3, and square root of 11 doesn't break down. How do I know it doesn't break down? Because there is no perfect square that is half of 11 or lower. Half of 11 is 5.5. The only one lower than that is 4. So 4 does not go into 11 evenly, so it does not break down. 1250. One rule is I can see that 25 goes into the 50, and there's a 25 right there. So I can say 25 times what number gives me 1250? Well, 25 times 5 is 125, and add on the 0. Okay. Now, here's another shortcut. I could break down each of those individually, or I could see what the GCF is between the two. The GCF between the two of them is 25. So I leave that as 25. I split this into 25 times 2. And 25, root 25 times root 25 is 25. And I have root 2 left, and there's my answer that quickly. Okay. So you gotta remember when you multiply any radical x times radical x, that equals x. It just takes off the root. Okay. All right. Now, just so you know, when I have a long or a large radical sum, I can divide it into, individual radicals. I can go vice versa as well. I can switch it back to a big one. They're the same. Well, square root of 1 is 1. And what you have to remember is I can't have a radical in the denominator. It's called an irrational number. So I have to rationalize it. Rationalize the denominator is what it's called. How do you do that? You multiply by the same radical again, because we know when you multiply by the same radical, it gets rid of it. So I have square root of 5 in the numerator over 5 in the denominator. I just got done showing you that root 5 times root 5 is 5. And 5 is a rational number because it can be written as a fraction. All right, now I could sit there and multiply by root 32 or root 32, or I could go ahead and break down root 32 into smaller. What's half of 32? 16. And break it down to 16 times 2, because then 16 gives me 4 root 2. And remember, I just can't have a radical in the denominator, so that 4 is fine. So now I'm dealing with a smaller number that I'm rationalizing, root 2 over root 2. Okay, and that's the benefit of doing this, of reducing a radical first. So now I get root 10 in the numerator, and remember, root 2 times root 2 is 2, times 4 is 8. And there's my answer. Okay, much simpler than going by root 32 over root 32, and then simplifying after that. You're dealing with bigger numbers. Okay, down here now, we are going ahead and again looking at, I can multiply the 11 times 2 because they're both outside, so that gives me the 22. And I see there's a 7 in both of those, the GCF. So I'm going to break 14 down into 2 times 7, and I still have that root 7 there. And don't forget, root 7 times root 7 is 7, times 22 gives me 154, and I have a radical 2 left over, and that does not simplify. So I'm done. I'm showing you these shortcuts, so learn them because other teachers don't always teach them. All right, 4 goes into 124. I know that because 4 goes in the last 2 digits. That's another rule. Okay, so 4 times what is 124? 31. 31 is a prime, so that's as far as it goes. Now, if you didn't know, when you have a root, that really means there's a 2 there. So now I go ahead and take my exponent and divide by that 2. So first off, I have 2 root 31, and 6 divided by 2 is 3. So the y cubed comes out. When I do 7 divided by 2, for this one, that gives me 3 remainder of 1. Remember, remainder from elementary school. Well, the 3 tells me how many I take out on the outside. The remainder tells me how many I have to put back on the inside underneath the radical. This number always has to be less than the root itself, which obviously 1 is less than 2. If that number was 3, for example, that means you didn't take as many w's out as you could have. So you just know when I have variables left underneath the radical, the exponent has to be less than the root itself. And there's my answer. Now, a side note is if I had the square root of x squared, if the exponent and the root are the same and they're an even number, 2 and 2 as they are, then you have to have absolute value around the answer. So that answer is absolute value of x. That's a tricky one right there. So just know that. All right, over here now, we have what's called, we have to multiply by the conjugate. Again, we have to get rid of radicals. So what I'm doing in the conjugate is setting up as if it's a difference of squares. We talked about difference of squares before. And why am I doing that? Because that gets rid of the middle term. Remember, difference of squares, there's no middle term. And I just have the first term squared and the second term multiplied together. The first terms multiplied together, that's 25. And the last two terms, plus square root of x times minus square root of x is minus x. And now notice there's no radical left. And then I have to go ahead and distribute that 6x through there. So I end up with 30x minus 6x root x in the numerator over 25 minus x. And there is my answer right there. Okay, let's go to the next one. Here I'm adding and subtracting radicals. So again, I simplify them. I start with half, since 32 is not a perfect square, I start with half the number. What's half of 32? 16. Isn't 16 a perfect square? Yes. So 8 times 4 times root 2 gives me 32 root 2 for that one. Minus 8 is half of that is 4, and that's a perfect square, 4 root 2. So now that simplifies to 2 root 2 times 4 is 8 root 2. Now I can put these together because the radicals are the same. That's like saying x. They're both x's. So I can combine by doing their coefficients. The radical itself doesn't change. 32 minus 8 is 24, and the radical stays the same, just like if it was x. That's like saying 32x minus 8x. That'd be 24x. Not doing anything with the x's. The x stays the same. Here I have 4 times 11, which then is 2 root 11 minus 1 root 11. Notice I put 1 in here because a lot of people forget that that coefficient is 1. 2 minus 1 is 1. Root 11 is my answer. Or you can just say root 11. Same thing. Okay, that means 1 root 11. Now, the other thing to know, oftentimes when you're adding and subtracting radicals, is you end up having to get the same radical in order to combine them. Okay, so if I simplify the smaller one first, or the one that's already simplified, so this, see how this 11 doesn't break down? Then I'm asking myself, there must be 11 that goes into that 44 in order for me to combine them. So 11 times what is 44? 4. So that's another helpful hint as far as that. So the smallest one to reduce here is the 18. What's half of 18? 9. That's a perfect square. 9 times 2. So it's 3 root 2. So if I'm going to be able to put one of these others together, there must be a root 2 in it, or I'll be able to put the other two together. Well, I should be able to see that's 9 times 3, which is a perfect square, and that gives me 3 root 3. So I'm not going to be able to put these two together. Oops, 3 root 3. But so there's either a root 3 that goes into 300 or a root 2 that goes into 300. Well, I know 3 times 100 is 300, and 100 is a perfect square. So that breaks down to 10 root 3. So anytime it's a multiple of 100, you use 100 since 100 is a perfect square every time. So now I can combine these two only because they have like radicals. So 3 plus 10 is 13 root 3. That's a 3 there, plus 3 root 2. And there is my answer. Okay, so now I have radical equations. I square both sides. That's how I get rid of the radical. Whenever any radical times itself gets rid of the radical. Well, don't forget I have to distribute this 2 through both. So that really says 9 times 5 is 45. Because root 5 times root 5 is 5, as we talked about. And I go ahead and take off that radical and get negative n. So switch it across to make it positive n, and switch that across. So n equals negative 45. Okay, here again, I have to square both sides to get rid of that radical. And that gives me 2x minus 1 equals 25. Add the 1 across, 2x equals 26, x equals 13. Always want to check to make sure it works. 26 minus 1 is 25. The square root of 5, 25 is 5. So that works. Here I'm doing reverse PEMDAS. Okay, that's how we solve all equations. So you know the order to do things. Add or subtract across first. So I add the 3 across. And then I'm left with 6, times root 3x over 2 equals 3. Next is division. So divided by 6 on both sides. And I'm left with square root of 3x over 2 equals 1/2. Now I need to go ahead and get rid of my radical. So I square both sides. And so I get 3x over 2 equals 1/4. Okay, then I can cross multiply if I wanted to. And I get 12x set equal each other at 2 and divide by 12 on both sides. And that simplifies to 1/6. Write that clear there. 1/6. Okay, there's that answer. Now over here, going to take a little more work. Square. And so if there's one radical, I get the radical by itself on one side, everything else to the other side, which it already is set up like this. So I get rid of this, and that just becomes x plus 5. But now I'm squaring a binomial. Remember, that's going to be a trinomial always. So that gives me x squared plus 2x plus 1 when I square that. Remember, the shortcut rule is you square the first term, that gives me x squared, multiply the two terms together, that gives me negative 1x, double that, and that gives me the negative 2x for the middle term, and then square the last term, negative 1 times negative 1 is positive 1. Now I have a quadratic. What's the first step of solving all quadratics? Set equal to 0. Since this coefficient is a positive here, I'm moving everything to the right side. If it was negative, I'd move everything to the left side, but it's positive. I subtract the x across, that gives me minus 3x. And subtract the 5 across, 1 minus 5 is minus 4. Set it equal to 0. Remember, a quadratic tells me I'm going to have two answers. Okay? But here's a hint. When I have a square root, and that's my, so this degree is 1. A square root is really the same thing as x to the 1/2. So the highest degree here is 1 on a variable. So it's going to usually tell you there's only one answer. But a quadratic means I'm going to get two answers. So I'm going to get two answers. It's pretty much guaranteed that one of those answers is not going to work. And then that's called an extraneous solution. So let's go ahead and factor that. It's nice, easy algebra 1 factoring, x minus 4 and x plus 1. Okay, set equal to 0. And set each factor equal to 0. X minus 4 equals 0. So x equals 4. Or x plus 1 equals 0 and x equals negative 1. Okay, so there's my two potential answers. Now I have to check them because there's a good chance only one of them is going to work. Okay, so if I take this off so it can easier to see to plug it in, substitute it back in. 4 plus 5 is 9. The square root of 9 is 3. 4 minus 1 equals 3. So that came out to be true. So this is a correct answer. Now I plug negative 1 in. Negative 1 plus 5 is 4. The square root of 4 equals 2. When I plug a negative 1 in here, I get negative 2. 2 does not equal negative 2, so it doesn't work. That's the extraneous solution. Extraneous, you see the key first 5 letters is extra. So that's what it means. Extraneous means an extra solution. Don't forget that because you'll hear that in Algebra 2 and on up a lot. Okay. And that does it. 13.5 minutes.